హలో హలో చెక్. హలో, వినిపిస్తుందా? రావట్లేదా? అందులో జూమ్ లో అన్మ్యూట్ చేయాలా? హలో హలో చెక్. కొంచెం హలో, టైం తీసుకుంటుంది. కొంచెం వినిపిస్తుందా? రావట్లేదా? అందులో జూమ్ లో అన్మ్యూట్ చేయాలా? హలో హలో చెక్. కొంచెం హలో, టైం తీసుకుంటుంది. కొంచెం వినిపిస్తుందా? రావట్లేదా? అందులో జూమ్ లో అన్మ్యూట్ చేయాలా? హలో హలో చెక్. కొంచెం హలో, టైం తీసుకుంటుంది. కొంచెం వినిపిస్తుందా? రావట్లేదా? అందులో జూమ్ లో అన్మ్యూట్ చేయాలా? హలో హలో చెక్. కొంచెం హలో, టైం తీసుకుంటుంది. కొంచెం వినిపిస్తుందా? రావట్లేదా? అందులో
Okay. So next we have a talk by Rajarshi Ray from the Indian Association for Cultivation of Science. So he's going to talk about SAT-REACH, a bounded model checker for affine hybrid systems.
Yeah, it should work, I guess. All right. So I'm Rajarshi. I'm a faculty at the Indian Association for the Cultivation of Science. And today I'm going to talk about a, a bounded model checker, SAT-REACH. Which it's a tool to verify affine hybrid systems. It's a joint work with my students Atanu Kundu and Sharthuk Das. Is it better now? Hello, it's better? Okay. So let me start by briefly introducing what is a hybrid system with an example. So consider that there is a robot and it has to navigate on a two-dimensional plane. The plane is divided into 9 cells. Each cell is a 1 by 1 square. So the robot has an initial positions. In our example, the robot starts from the origin 0, 0. And each cell has a predetermined velocity that is assigned. So for instance, in the green cell, the robot can move by taking a velocity, which could be any velocity given in a range shown in the diagram from left to right. And in the rest of the cells in this example, there is a unique velocity that the robot can take, which is shown by the velocity vector, right? So this constitutes the continuous dynamics of the robot, how the robot is going to move in each cell. And there is a discrete dynamics also in the system, which is essentially which essentially says how is the robot dynamics going to instantaneously change when it moves from one cell to the other, right? So when for instance, when the robot moves from cell 1 to cell 6, its velocity instantaneously changes to the velocity at the destination cell, right? In this example, the velocity downwards. In this example, one of the cell is marked unsafe, the red color cell in this example. And we want to know that under this given dynamics of the system, can the robot navigate safely, right? Can it move around without going to cell number 4 at all? Right? So such kind of systems are called hybrid systems due to the combination of continuous and discrete dynamics in place. And these kind of systems could be mathematically modeled using a hybrid automata, which is shown on the right. So the way we can model this system is that we assign each cell with a location of the automaton. So for instance, the green color cell is mapped to location number 1 on the right. And the continuous dynamics of the robot is marked by differential equations in the location of the automaton. So for example, here we say that the velocity in the x1 direction could be any value in the range of minus 0.6 to 0.6. The velocity in the x2 direction is exactly equal to 1.2 when it is navigating in cell 1. And similarly, for other cells, we have corresponding locations in the automata and their corresponding continuous dynamics. The discrete dynamics of the system are captured or modeled using the discrete transitions of the automaton. Here, if you let's consider the example of a transition from 1 to 6. A discrete transition comes with a guard condition, which says what is the prerequisite for the robot to make a move from cell 1 to cell 6. So here the condition is that the robot can make a move only when it's on the boundary of cell 1 and 6, which is given by the constraint that x1 should be equal to 1 and x2 should be any value between 0 and 1, right? So that way, for all the 9 cells, we have a corresponding automata with the corresponding transitions. Okay. Let's look at a typical execution of a hybrid system. So hybrid systems execution is an alternating sequence of continuous and discrete transitions. So in our example, the robot starts at 0, 0. It makes a continuous move by moving along a direction that's shown with mark C. That's a continuous dynamics. Then it instantaneously changes its velocity to the velocity marked in cell 2. So that is marked by the discrete transition D here. Then it moves to the, then it takes the continuous dynamics in cell 2, so moves in certain velocity, and so on. So in the last figure at the right, we have a trajectory or an execution of the robot in depth 2. So here, I mean, the depth here means how many discrete transitions does the robot take place, right? So here we have 2Ds, 2 transitions, 1 to 2, 2 to 3. So that's why it's a depth 2 execution, right? So our problem statement is now as follows. So we are given a hybrid automata model of a hybrid system. The dynamics of the system could be of the form x prime is equal to ax plus u, where u is any vector in the set of, in a bounded set capital U. We are given an initial condition and a forbidden condition as linear constraints. We are given a bound on how many discrete transitions can be taken, and we want to now decide whether the system is safe. That is, can we ensure that all trajectories, all executions of the system are safe? Okay, so the bounded model checking in the literature, so there has been 2 broad approaches to solve this problem. In one approach, the hybrid automata is encoded in a SMT formula as a SMT encoding together. So the encoding takes the automata, the bound K, the negation of the safety property, and there is a delta approximation factor which is taken as input. And the formula is such that if it is satisfied, then it implies there exists a continuous trajectory of the system which violates the safety property. And if it is unsatisfiable, then there doesn't exist any such trajectory, and we can conclude the safety of the system. So here I note that if the formula is satisfiable, we say that the safety of the system is unknown. That's because of the delta approximation factor, which essentially encodes additional trajectories which may not be part of the actual system. So that's the over approximation factor, and due to this over approximation, even if the formula is satisfiable, we are not sure whether that trajectory is real or spurious. In the other direction, the automaton is fed to a reachability analysis engine together with the bound K of model checking. The reachability analysis engine computes the set of all possible states reachable under the dynamics of the hybrid automaton. And this reachable region now could be checked with intersection with a given unsafe region. If there is no intersection, we conclude the system is safe. And if there is an intersection, again, we know we cannot conclude about unsafety because the reachable region is over approximation of the exact set of states calculated. So we have an unknown result on safety if there is an intersection with the unsafe state. Okay. Sorry. The first is on the left side. Right, so the encoding is, so the automata's dynamics is encoded as a quantifier-free nonlinear arithmetic formula, which allows ordinary differential equations to be given as constraints. And there is a delta factor which relaxes the constraint. So it adds additional trajectories, it allows additional trajectories to satisfy the formula. Right, so we need this delta approximation because the exact reachability analysis problem for hybrid systems in general is undecidable. So unless you have. Can you say again? Mm-hmm. So the bound k is part of the input, right? So k is given, right? So if k is okay, so you're saying, can we conclude whether if the system is k safe, then it's k plus 1 safe also, something like that? Right. Correct. Correct. Yeah, but the formula will keep on increasing. But what about, so we want to know for k equal to infinity to say that if you don't want to do bounded model checking, we want to. Right. So here, so what is the question? I'm yet not very clear. Okay. So okay. I think the over approximation there is over approximation because we are in the real domain. So yeah, so that's all I know. Okay. Right. The example that I've shown is piecewise linear, but the tool works on a more general dynamics, which can have affine differential equations also. So if it is piecewise linear dynamics, then bounded model checking is decidable. Then the formula turns out to be a LP for general hybrid systems. So for affine hybrid systems also, it's undecidable. And so okay, so let me then let me quickly talk about our approach of SAT-REACH. So we have three components. In the first component, we take the hybrid automaton and we take the graph out of it. So we throw away all the continuous dynamics, just have the graph and we encode that graph as a propositional logic formula. The encoding is such that if the formula is satisfiable, it implies there is a path from the initial location to the destination unsafe location in this example. In this first higher abstraction, if we see that there is no path existing from the source to the forbidden location, then we can directly conclude the safety of the system, right? Without further analyzing the continuous dynamics in place. So that was the motivation why we wanted to separate this layer out. Now, if we do have a path in the automaton, then we want to check whether that path is actually realizable or not under the continuous dynamics. So we bring in the continuous dynamics along the path and we run a reachability analysis along the path. Now there could be two outcomes. If the reachability analysis tells that the path is infeasible, then we have to move on to the first part, and first we need to call the SAT solver again, get the next possible path and so on. And if the path turns out to be feasible under the continuous dynamics, we again need to check in the third component whether there actually exists a concrete trajectory or not, because of the over approximation in the reachability analysis computation. Right. So let's take an example of a quick run of our algorithm. So let's say the SAT solver, it comes up with a path 1, 2, 3, 4. We call the reachability analysis engine. The reachability analysis gives us the gray colored reachable region, which doesn't satisfy the guard condition for 2 to 3 transition to take place. So that means that the path is infeasible, right? We then continue with the next path. Let's say that's 1, 2, 4, 5 returned by the SAT solver. That again turns out to be infeasible. And finally, we have a path 1, 2, 5, 8, 9, which actually reaches the destination, the forbidden region. And therefore, we need to further analyze it for existence of a concrete trajectory. Okay, do I have time? So 2 more minutes, okay. So then let me not go into the details of how we find out a concrete trajectory. So basically, we map it to a nonlinear optimization problem. If that optimization problem gives us a 0 minimum, that implies presence of a concrete path. So briefly, the search is over segments of trajectories over the locations of the path. And the cost function takes the distance between the segments, right? So the segments could be disjoint. And we want to take the distance. If we can minimize the distance between the segments to 0, that means there exist pieces in the locations which one could splice together to get an actual trajectory in the automaton. So that's how the segments are should follow the actual dynamics in each location, right? So we take pieces of segments, right? And we want to search pieces in such a way that they join together and make a complete trajectory of the automaton. One location, correct. So here are some results. This is the result on a 25x25 navigation benchmark on our tool. So we can see that with our tool, the search computation is much more directed. So the black color region is the SAT-reach output. In comparison to, let's say, a breadth-first exploration of the state space, which is shown in gray color. So it goes up in various directions and therefore has extra computation. So that's another example on the right. So BFS explores this additional 2 branches, which we don't do in SAT-reach because of our first higher level abstraction, where we first find a path and direct our computation along the given path. All right. So we compared our tool with DReach, that is that encodes the problem into an SMT formula. We tested on 32 unsafe instances, and we could solve for 29 of them, where DReach could solve only 16. For safe instances, we could solve all of them, where DReach timed out for most of it. And also, we compared it against breadth-first exploration, and we were better. Okay, so thank you. The tool is available online.
We have time for one question.
Can you briefly explain your refinement approach?
Refinement idea? Here. So the first abstraction is you take the graph only of the automaton, right? You throw away the continuous discrete dynamics. So you take a path, you get a path from the SAT solver to the unsafe location, right? So in the second step, you want to check whether that path is feasible. So here you do a refinement by bringing in the continuous dynamics only along the path, right? Not the entire automaton's continuous dynamics, right? So then you check feasibility of the path. If it is feasible, then there is the third refinement, which is the optimization problem I talked about, where you check whether there is actually a concrete trajectory within the computed reachable region.
So by refinement, what I meant was that if even that, if you check this as using an OOPD, like whatever solver that you use, and it says that this path is not feasible, do you use that information to refine your first query?
Oh yeah, so we do that. Yeah, I didn't say about all those optimizations, right? Okay. So if my path is infeasible, I find out the smallest piece which is infeasible, and then I give this information back to my solver to exclude
back as a constraint in the SMT solver.
Yeah. So basically, I give back the information from feasibility analysis back to my solver so that I can prune the search space.
Thanks.
Okay, thank you.
Okay, so next we have a talk by Inzama Mulhaq from IIT Kanpur, and he's going to talk about counterexample guided imitation learning of feedback controllers from temporal logic specification.
Yeah. Good morning, everyone. Am I audible? Yeah. So I'm going to present this training approach to imitate these feedback controllers. And this is our joint work with Professor Thao Deng, who is from Merrimack, Alexandre Donze, who is also in France, and then Nicolas Kekatos, he was earlier postdoc there, and then Professor Indranil Saha from IIT Kanpur. So to start with, I'll show you the state feedback control, where there is a controller, like for example, MPC, and there is a plant, and then there is some reference which has to be tracked, and this Y is the output of the plant, and X is the feedback to the controller through the controller. Yeah. So now in R is the reference. Basically, there is a trace which you want to follow. So this is kind of a reference tracking problem. So MPCs are known to be, I mean, because they solve non-linear optimization problem, they are costly. And so what we want to do is, can we have a neural network over here in place of this MPC controller, which is comparably faster than the MPC. But another condition which we want to have is that it should be reliable. So this is what we want to come up with. And for that, before going further, let me briefly introduce the running example which I'll use. So this is the plant or system where there is this is a flying robot which we have taken from MathWorks. And this is like, we can call it kind of an artificial example made out, because this two-dimensional flying robot. There is no third dimension, and there are these two thrusters which actually generate the thrust. So U1 and U2 are the thrusts, and this theta is the angle of the orientation, or you can call it, yeah, thrust angle. So what this system has, meaning what is the goal in this system is that from any position in the 2D space, what we want to achieve is that it should reach the origin with this theta angle to be 0. So that is the problem. And U1, U2 have to be controlled in such a way that this goal is achieved. So this is the example. Now, there are already a few approaches, training approaches, to come up with a neural network which can somehow imitate the MPC controller. So for that, there is the very basic approach, initial approach was the behavior cloning approach, where you just run the MPC controller and get the data of the input and the output. Basically, the control input is coming, meaning you are getting this Y, and on that Y, sorry, this X, and what is this? So the correlation between X and U. So that is the data, and you just train the neural network using the normal training approach by defining some loss function. So this is the result which we did, in meaning which we implemented this approach in the MATLAB, and we found this. So this is just a counter example, basically saying that, so this x2, if you can see, I think it's not very clearly visible, but this red line, if you see, that is the MPC, which is at 0, meaning it is stabilizing at 0, but the neural network is deviating from there. So this is one counter example to the for showing that neural network is not working properly, at least for this particular initial state. So the idea is that it needs more data. So in 2011, there was this approach, which is also another standard approach in imitation learning, and it's called Dagger approach, where what they do is they generate data in a loop. But what do they do is at each iteration, they will generate new data, and then using that new data, they will retrain a new network. And what they do is, for each previous iteration neural network, they will simulate it, and with each step in that simulation, they will again run the MPC, which is the kind of a teacher for the neural network. So this is the Dagger approach. And for this particular example in MATLAB, we ran it, and what we found out is we ran it for 140 iterations. Meaning, so this example has been actually presented by the MathWorks on their website. They have put it. So this ran for 140 iterations, and it gives for a particular input, it runs very well. But when we tweak it, we again get some counterexample. And even if we assume that it's doing fine, so for our community, the question is, can we trust it? So for that, we came up with our approach. And there are two interesting questions over here. So those are, first of all, how to express the correct behaviors. And second, how to say that a particular neural network is good enough or is better than another neural network. So I'll tackle these two issues first, and then we'll go to the approach. So to express the correct behaviors, STL is signal temporal logic is very much used in control systems. So this signal temporal logic is just like the LTL, but there are two extra things. So one is the predicates are like of this structure, where YT is the signal with meaning having values at each time point t, and G is some function on it, which gives a scalar value as output. And then there is a comparison whether it is greater than 0, less than 0, or equal to 0 or not equal to 0. So this is the structure. And then the other thing is that there is an interval, because in signals you have these. For example, if you want to specify stabilization property, you want to say that it should stabilize within certain time period. So to express that, they have added this interval. So this is so this interval is extra in the normal LTL formula. So this is signal temporal logic syntax. I will show some examples just to, most of you may be knowing about it, but let me go through it quickly. So for example, this is a signal, and we can say something like always. So this is normal LTL, but this scalar valued function is there. And then now comes the interval part, where we want to say that between 2 to 6, that is, so each of these box is 1 unit. So between 2 to 6, this signal xt is always less than 2. So that's true for this particular part of the signal 2 to 6, right? Now, maybe one more example, and I'll finish here. So this one, we want to say that signal is stabilizing. So to say that, what we say is whenever there is an overshoot, basically the signal is going beyond certain point, that is more than 0.5. It comes within a certain period of time, it comes back to the stabilization zone. So that is what we are saying. Whenever xt is becoming more than 0.5, meaning it is going beyond this, it should come back within 1 second one time unit, it should come back to the origin, meaning around the origin. So xt is less than 0.5. Yeah. So these are the STL examples, but in many systems these are kind of parameters also, meaning how much this time duration in which you want the system to stabilize, how much it should be is not, meaning that is dependent on the designer. So those things can be parameters in some systems, right? And similarly, what will you define as overshoot? That is also a parameter kind of thing, right? So for that, there is something called parametric STL formula, where the numeric constants in such formula can be variables or arbitrary constants, we can call them, right? So for example, this is the some formula where you want to parameterize this 2 second and 3, right? So which can be like pi and tau, right? So this whole formula can be also expressed as a parametric STL formula. And then you can have a valuation for the parameters to see whether that particular parametric STL, that valuation and the meaning is satisfying, meaning the signal with a particular valuation is satisfying the property or not, that can be seen. So now, so this is an example property which we have used in our work, which is actually the parameterization of the property which I showed in the beginning of the stabilization, right? Yeah, so maybe I'll finish soon. Yeah. Now, the second issue was the quantification. So this is a little more involved thing, but anyway, I'll quickly go through it. So what we do is we divide. In the specification, yeah, we don't know. Meaning sometimes you know, sometimes you don't know. But the point is that meaning it depends on system to system, basically. Those values. No, so in this particular work, we are not going to find those values. So basically, STL is good enough to specify the property, and PSTL we are using it for something else, which I'm going to show now. So here, so our comparison metric is based on that. So here we have this distribution of the parameter space. So if the property is, meaning phi is monotonic, then the validity domain, there are two validity domains, meaning the formula is valid in this particular domain and it is not valid. So this is actually, if the formula is monotonic, there is a Pareto front structure to that. So this is a work done, I think I have not cited it here. This was done in, I think, 2011 by one of our collaborators. So X is so V is the valuation, X is the signal. Right. Monotonic means the parameters are like, so for each parameter, the formula is right. Right. Yes. True. So this is the false domain. I'm going to show it. Yeah. So this is the false domain, and then this green one is the valid domain. Now, so what we say is, for the formula for controllers for which this domain, false domain, is similar to the false domain for the MPC controller, then that controller is very close to the MPC controller. So that is the basic idea which we have. So now computation of the volume of this box, because I am showing it in 2 dimensions, but there can be multiple dimensions. So this is a box, and so we need to find the volume of the false domain. So if false domain's volume is comparable to the false domain volume of the MPC, then the controller is good. So the computation of volume is a problem, but it can be approximated because of this monotonicity. Right. All this is for a fixed size. All this is for a fixed signal. Yeah, no. So here I think this mistake is there. So we calculate this domain for. So we say that this for a valuation is satisfying a particular, meaning a controller is satisfying. We define that actually. So here I am showing signal, but this can be done for a controller, and we define that as for all parameter, for all valuations, this is satisfied. So that is the idea. So this we just count the we under approximate the false domain by just finding out the boxes which are points, which are, meaning we just calculate the volume of the these hypercubes. So this is the idea, and then now training approach we do certain. I'll quickly go through it. What we do is we have these. So this is inspired by the dagger approach, where we also go into a loop. But what we do is we have these specifications. So initially we find the data from the nominal controller, and then so this get init samples is finding the initial states randomly, and then the MPC controller or any other controller has to be simulated, and we get the initial data set. We train the neural network with that, and then get the first neural network, and then we falsify that particular neural network. Once we have that neural network, we falsify it. Falsify meaning there are tools which can find out which can dynamically run the controller, meaning simulate the controller, and then find out the counter examples with given property. So we do that, and then there is a step. So there are two things. One is grid coverage, and the another is finding out counter examples. So grid coverage is the initial training. When we do it basically, we divide the state space of the system in these grids, and we take 1 point from each of these cells. So that's the basic idea, and we don't, when we get another, so that is the grid filtering part, where we don't take more than 1 point from the same cell, and that we do even when we have counter examples. We do the same thing, meaning we don't whatever cells we have covered, we don't take those cells again, so that the original data which we had found is not corrupted again by the new data which may be wrong. So in counter example extraction, what we do a similar thing from. So this red thing is a counter example, and what we do is those cells which are outside this, we are running the MPC from there, and then adding new data to it. So that's the idea of data extraction. Now coming quickly, so this is already done, I think, and this was the result. Meaning in the initial iteration we had this Pareto front. So this red thing below is the nominal MPC controller Pareto front, and the first iteration, the Pareto front was something like this, where it was kind of a superset of the false domain of this one. So in fifth iteration it came close to here. Now one question which is still I'm thinking about it but not very clear about it, why there is a meaning this overlap or intersection between the false domains of the nominal and the neural network is there. So that is still remaining. So now to conclude with, we have this efficient data set aggregation approach inspired by Dagger, in which we added grid coverage and grid filtering part, and we also had this measurement of goodness of controllers. Now in future we want to merge these two approaches. So these two things meaning and get a single training algorithm where we just begin and it should stop somewhere using this goodness part. So that is we are working on it. And the second thing is, this is very interesting part, and I'll finish with it. So in controllers we have these complementary properties. Basically if there is a high overshoot, it will not stabilize very soon, but if it stabilizes soon, it meaning higher less overshoot with early stabilization, is not possible, meaning that we don't find usually. So these two are complementary properties, right? So can we have a neural network which can get data from both the kind of controllers, and then it can have best of both? So here I finish. Yeah, thank you.
So we are out of time. So maybe if there are questions, we can take it offline. But we'll have a short break now of 10 minutes, and we'll come back at 11:45. Thank you.
So welcome back, everyone, after the break. So we will have 3 talks in this session by Umang, Sanjana, and Aditya. Okay, so let's begin with the first talk by Umang. He's going to talk to us about sampling for dynamic erase detection. Over to you.
I am Umang Mathur. I'm an assistant professor at NUS. And I'm going to be talking about concurrency and concurrency bugs and basically how to find them efficiently. When it comes to concurrency, I don't need to talk a lot about why we care about it, especially to this audience. It's a ubiquitous computing paradigm. If you look at, browsers or operating systems, or even the modern, AI sort of things, they're all backed by, concurrency-centric advances behind them. But at the same time, even till date, writing concurrent programs is challenging. That's because, when developers write programs, they have to reason about these, and traditional ways of reasoning do not necessarily work very well for concurrent programs because they have to reason about all possible thread interleavings, and then even if you have a small number of threads, this kind of reasoning really blows up. So that's not ideal, and because of this, a lot of concurrency bugs show up in large-scale software systems, and because of that, we've seen in the past loss of money and also loss of lives. So bottom line, we want to avoid that. Yeah. Sorry?
Ariane, I presume that's Ariane. Why did you consider that as a concurrency bug? I mean, the system failed very reliably.
Okay. So I will go back and check. Thank you. Yeah. All right. So so talking about concurrency, I think if we want to ensure reliability, the first point of defense is really to develop techniques that can help us detect these bugs. And when it comes to techniques, there are 2 sort of broad classes of techniques that are out there and are used popularly. One is the class of static analysis techniques, where one looks at source code and then tries to analyze the source code and infer the presence or absence of bugs. A common problem with these kind of techniques is that the annotation burden is too high, and the second thing is that there are a lot of false alarms. So when it comes to deployment of such tools, they take less priority over the dynamic counterparts, where one looks at executions and analyzes executions and then tries to infer bugs, right? And typically, it's possible to make these techniques sound. The other benefit is that they are also, they're very fast. In fact, most of the popular bug detectors out there are mostly dynamic analysis tools. And that's also what I'm going to be talking about. And this is, in fact, part of a larger research program that that I have decided to take on. So my focus will be on detecting data races. So data races are basically these problems which occur when you do not have proper synchronization in your program, when 2 threads try to access the same common memory address, and without, they don't synchronize properly. So dynamic analysis techniques, I just want to sort of emphasize the fact that they're so well developed today that the LLVM compiler gets shipped with like a race detector with it. And in fact, most software developers routinely use such techniques. So because my talk is going to be about how to do better than the existing dynamic analysis, let's talk a little bit about what is it that they're really doing. So I'm going to be talking about concurrent programs. So they look like this. This is an example of a Java concurrent program. You have two threads. Here there are also memory addresses that these two variables read and write to. So that's a form of communication. And then there are also constructs like locks, which help you, let's say, enforce mutual exclusion. And then, because I'm going to be talking about dynamic analysis, I will necessarily be talking about executions, and that's what executions look like. They are essentially sequences of events. Every event tells you what is the thread it came from, and also what is the operation. So for example, if you look at event number 1, that's an acquire of the lock L by thread T1, and event number 4 is the read of variable X by thread T2. Okay, so my focus will be on a particular kind of data race detection, which is called race detection based on the happens before partial order. Let's just quickly look at it. So happens before is this partial order that you construct on an execution. Specifically, if you have an execution, you can construct this order on this set of events of that execution. So this is given as this in terms of these two rules. The first rule says that all the events inside a given thread are ordered in the order in which they appeared. And then after that, you also order critical sections. Namely, you order the release of an earlier critical section on the same log before a later critical section of that log, before the acquire of the later critical section of that. So here is an example. The blue edges are due to rule 1, and then the red edges because of rule 2. So of course, it's a partial order, so it's also transitive. And now, based on this partial order, you can also detect data races. You can say, I'm going to look for two events which are conflicting. By conflicting, I mean this pair of events access the same memory location, and not both of them are reads, so at least one of them is a write. And these two events are also unordered by this partial order. Okay, so that's how you detect data races based on happens before. Now, of course, you do not necessarily explicitly construct this partial order. You do a little bit fancier thing. So, in order to sort of quickly understand what is the algorithm, the algorithm for detecting data races based on the happens before partial order runs in a streaming fashion where every event is analyzed as it is generated, and then you sort of maintain some extra metadata, and you keep updating this metadata. So the precise metadata that you require here is called as the timestamp. In particular, for an event E in your execution, you try to compute this timestamp. So timestamp is like a vector or a function that maps the threads in the execution to some number. So in particular, if I look at E's timestamp, and if I look at the Tth component, then it points to, then that value is the last event in thread T, is the number of events in thread T that E is aware of. By aware of, I mean because of an ordering in the happens before partial order. Okay, so at the end of the day, we try to use, I mean, these race detectors try to use this property. That is, if I want to capture the happens before partial order, I can do that by just computing these timestamps. So that's what the algorithms do. They compute these timestamps on the fly, and then they sort of identify data races. So capital E. You're right. So it should be small e. Thank you. Yeah. So just to sort of be very concrete, here is an example of an execution. A race detector would assign timestamps as follows. In the beginning, acquire L would get the timestamp 1,0. It denotes that it's an event of thread 1, so it knows of first event of its own thread, so that's why this component of 1. But it doesn't know any event of the thread 2, so that's why this component is 0. Similarly, you do read of X, and therefore this component becomes 2, and the other component stays 0. Here, this becomes 3, 0. And now notice that this to this is a happens before order. So the timestamp of this event is basically 3, 1, because it knows of 3 events in thread 1, and 1 event because this is an event of thread 2. And likewise, yes. You can do better. you can just increment at acquires and releases. It just releases for the purpose of, for the property that we're testing. But roughly that's the idea. You essentially do a lot of timestamp computations. By timestamp computations, I mean increment of some component, or here this is implemented using, so this is, you can think of this as a channel. So you send your clock to a channel and then this guy receives it. And the way you receive it is you sort of read some timestamp and you join it with your timestamp. By join, I mean you do a pointwise maximum. So this happens while you're executing. So the overall picture is that you have your software, you're running your race detector, and the race detector observes all of these events from multiple threads, and it sort of, in some sense, serializes this execution. And at every event, it sort of, updates some of these timestamps. It maintains a finite number of timestamps. It doesn't necessarily sort of stores these timestamps. They are logical clocks, not Lamport's, but more like Matterns or the other clocks. Lamport's clocks are a little bit different. They are scalars here. But yeah, these are the standard vector clocks that any distributed systems course will teach you. So you do not explicitly recover the ordering for all pairs of events. You sort of say that if I'm interested in detecting a race on the variable X. And so you maintain an additional vector clock for X. And then you say, I'm going to sort of maintain the vector clock that represents the last event on X. And when I'm doing a new event on X, I just do a comparison with that last event. And that suffices to detect data races. Earlier one should not dominate this. Neither one of them, they should be unordered. Then it's a race. Otherwise, the later one is larger. Is smaller than the new one. Yeah. So if you're looking at some events, I mean, let's say 2 events, E1 and E2. If you want to check if E1 is smaller than E2 according to the partial order, or according to the timestamping order, so you're right that, so naively you can check that the whole timestamps are comparable. If you want to do a more optimized check, you can say that the T1th component of the first event, T1 is its own thread, is known to the second event. So the second event's T1th component is bigger than that guy's T1th component. Anyway, so the point of all this exercise was to sort of hit home this point that at every event, you end up doing a lot of computations. Namely, you increment some counters, or you take these maximum operations. And when it comes to real world software out there, like browsers, if I run a browser for 1 hour, it'll give me 1 billion events. And even if a browser is sort of reasonable browser and it's running on a large scale system, even if I run a browser on my laptop, I will at least have two threads. Then the number of operations that end up being performed when I run the race detector are going to be extremely large. And in fact, race detectors are known to suffer from this problem. And in fact, even the official documentation says that, don't hope for performance when you're using race detectors, okay? Think of race detectors as if they're completely in the testing phase, and not just completely in the testing phase. You should only use them, let's say, when you're doing some overnight tests. So that's what I wanted to look at, and I wanted to understand if we can improve this. And when you think about this problem, sampling comes to mind. Okay, that's the first thing that one tries to do here. By sampling, I mean, as you're observing execution, you don't perform these events at every event, perform these operations at every event. You only selectively do these updates. Okay, so that's what I mean by sampling. So something like this. I decide to observe some events and ignore some events. So when you're trying to do this sampling, I mean, you have to be careful. In particular, naive sampling algorithms may end up being not sound. By sound, I mean an algorithm is sound when it only reports a race when there is one. Similarly, if you're trying to sort of balance soundness, you might end up sampling too many events, and therefore you won't have any benefit of sampling. And finally, you also want to ensure that overall the probabilistic the guarantee that this algorithm provides is also reasonable. You don't sort of end up not detecting a race at all. So that's what we wanted to come up with, an algorithm that balances all of these conditions. So this is the soundness in the
race detector sound. If there's a race, it detects it.
So this is the bug detection side of things, where my goal is to detect a bug, and I'm not interested in false positives, right? So I want a sound bug detector. Yes, we don't want any false positives. Yeah, you're right. So this confuses many people. Okay, so just to get a sense of how does one sample, let's try to sort of do some simple sampling. So, okay, the colors are not so visible, but here I tried to shade the first event, saying that I want to observe the first event, and then I want to skip the next two events, but then I want to observe the later event, namely the acquire and the read. Okay, so here is what might go wrong. I mean, here is what will go wrong over here. Because I'm not observing these acquire and releases in thread 1, it so happens that the acquire L over here will not know that any of the events in thread 1 are known to it, because it's missing this synchronization. And therefore, when it comes to read of X, it might end up saying that it might end up concluding that this read of X and that other read of X, think of it as the write of X, are in race. Right? So you can't be just completely naive about how you sample. You have to be a little bit careful. And the essence here is that if you're skipping, you cannot just skip synchronization events if you want to ensure soundness. You have to essentially maintain synchronization events. You have to sample synchronization events. And so is it the case that we should sample all synchronization events? Well, actually, in the literature out there, there used to be this sampler called light race proposed by some people at Microsoft, which essentially worked like this. They looked at the execution, and then they sampled every synchronization event. So if you look at the green event, here is where I'm going to make a decision. I'm going to see if this green event is a synchronization event. If so, I'm going to necessarily observe it. I'm not going to skip it. So by synchronization events, I mean acquires and releases. That's all. For the happens before order that I defined, those are all the synchronization events. But when I see an access event, by access event, I mean a read or a write, I can decide to sample it or not with probability P. And that's what light race did. And it's a sound algorithm, although in the worst case, it does sample linearly many events. And every race it detects with probability P square. Okay, since I'm short of time, I'm going to sort of skip this one, which is this other algorithm. It's called Pacer, where again it decides to look at all synchronization events, but then when it comes to detecting races, it does something that's a little bit clever. But at the end of the day, it's also sampling linearly many events, and the probability guarantee is a little bit better, and of course it has some optimizations. Not so important. I want you to focus on the fact that the two known algorithms sample linearly many events, and the question I would like to ask, or we asked at some point, was, can we do better? Can we sample sublinearly many events and still ensure soundness? So that's where we looked at the theory A literature, which is the other track downstairs, and we looked at property testing. So for those of you who might not have heard of this term, property testing is this style of algorithms where you try to design algorithms for testing some property, and you try to ensure that your algorithm samples as little as possible. So we try to understand. So that's what we also try to do with this problem. And to this, let's try to sort of look at what is it that we are really doing. We want to design a property tester. We designed a one-sided property tester. So a one-sided property tester for a language L, think of language L as some property, is basically some randomized algorithm that meets the following obligations. First of all, it has small query complexity. Second, it's one-sided, meaning whenever the input is in the language, it necessarily says yes. Now, when the input is not in the language, you're allowed to make some error, but you have to guarantee that when it's far away from the language that you're looking at, you have to give no answer with very high probability. So epsilon and delta are some parameters. Okay, so that's what a one-sided property tester is. And essentially, we designed a one-sided property tester for race detection. That is right. Yes. So we looked at Hamming distance. Okay. So the overall design of our property tester, which we called RPT. RPT stands for race property tester. It basically works as follows. As you're observing executions, yes. That is right. So that is right. So we want to design a sound algorithm, and we want L to be race-free executions. That's right. So the algorithm is pretty simple, as with all randomized algorithms. It sort of, as the execution is running, it samples a number R, which denotes that I'm going to be looking at R subtraces of my full trace. And I will also ensure that each of the subtraces that I'm going to look at is going to have a constant length. So both R and K are constants. That means they're independent of the length. So in short, this algorithm, okay, so now once we have these subtraces, I'm going to sort of independently analyze each of these executions and detect data races on just these subtraces. Okay, so as you can see, I'm only sampling constantly many events, and it has this epsilon delta guarantee that I showed you before. So bottom line is there is a sublinear algorithm that we came up with, which has this nice probabilistic guarantee. R and K are constants. They're only dependent on these epsilon delta parameters. And some meta parameters like number of threads and locks. Okay, so that's the guarantee. It's basically a rephrasing of what I told you before. K is some constant that is only dependent on epsilon. R is another constant that depends on epsilon and delta. And with these parameters, RPT has the guarantee that whenever you give it a race-free execution, it will say it's race-free. And whenever you give an execution that's far away, meaning it is in some sense reasonably racy, then it does give a yes answer with probability 1 minus delta. Okay, so I was hoping to. Yes, so I was hoping to go through this, but okay, so maybe let me go through the epsilon far distance. Okay, so that's the distance. So you can define the distance between a string and a language by first defining the distance between two strings. You can say, this is the Hamming distance. If the strings have the same length, then it's the Hamming distance. Otherwise, it's infinity. And therefore, the distance between a string and a language is basically the closest string in that language. And so when I say epsilon far, I mean epsilon times the length of the string. Okay, I'm out of time. I think, okay, let's conclude this now. So are there questions, or I can continue for 5 more minutes? Okay, good. Sure. I think the bottom line is that it works very. Okay, this was a proof. Was sort of interesting and simple, but I think the bottom line is that it works in practice. And the green one is the one that this is the RPT, and you can say that the run times are very fast as compared to this other sampling based algorithm, or also this non-sampling based algorithm. And if I do a fine-grained analysis of what is the time that I spend in these vector clock updates, that is indeed a constant, which is expected. And as you can imagine, the probabilistic guarantee only gives you certain things, meaning only when you are very, very racy, you're going to detect many, many races. So that's also true in practice. But yeah, to conclude, I think I've already made all of these points. I think in the future, it would be interesting to see if this algorithm can be extended to make it distributed, because vector clocks actually run in a distributed fashion and not in a serial fashion. And to see if something similar can be done even for other properties like LTL. If you're doing runtime monitoring against LTL properties, I'm sure you can do something similar there as well. So I think with that, I'd like to conclude. So there are no false negatives. So that's what this. So when most of the times we did not miss any race. The only time we missed races were when the races were either very few, like one race in a trace of billion events, or when all the races were really far, like meaning the two events involved in the race are like the first event occurs right in the beginning and the second event occurs millions of events later. So those are the cases where we miss out on races. But otherwise, the way I think of this is like it's a good tool for developers to sort of do some initial runs and quickly discover a lot of races. And then if you want to do heavyweight techniques, you can do that afterwards.
Yeah. So, questions?
So, so this is the pack style guarantee, right? Pack style guarantee.
No, it's not pack style. It's for every execution.
Yeah, can you show the slide for the guarantee?
This one. Oh, is that what you mean?
Yeah,
yeah. Yes.
Yeah. So yeah, it reports a race with probability 1 minus delta. So I mean, really, when you want to implement these kinds of algorithms, you have to repeat it a
That
few
is right.
times.
So we did do repetitions. Yes.
Okay. So you get an execution trace and then you repeat this.
So you're saying in practice also should I repeat?
Yeah.
So in our evaluation, the observation that we had was that most of the times, all of these runs really yield the same thing. I mean, in terms of checking if there is a race. If you're really interested in a more fine-grained answer, then yes, you should report it. You should do it multiple times. I mean, anyway, these are like dynamic approaches. You must anyway run multiple times. Because on one execution, you might see on one run, you might see one execution. And on another run, you might see a completely different execution. So
one execution to run once.
That's right. Yeah.
Are there any approaches of hardware runtime monitors for blindingly fast?
That there used to be some line of work like 15 years ago, but I think soon, very recently, it has gotten back again, where a lot of recent advances in hardware like fibers and stuff like that, they help you reduce some overhead, but nevertheless, it's still pretty slow. I mean, if you look at race detectors, the ones that are professional grade, they are very slow. The other thing with hardware is that you cannot just ship it as a software, then you have to integrate it with your hardware.
No, I mean, there's programmable hardware.
Sure. So that I have not seen so far. Yeah. I think something around 0.01 or 0.001, one of these. I think we experimented with multiple. Yeah.
Okay.
Yes, the total runtime was much less. That is right. Yes. No, there is a external sampler. At runtime, we sample.
Okay, I think in the interest of time, we should, thank the speaker.
Thank you.
And Sanjana,
Oh, this is just
set it up. In the meantime, I'll use this time to ask a question.
Yes.
So on a very different note, on a very yes.
I think this is mine. I think you had another one on the table. Oh, microphone. Okay.
This execution, right, is like is a POSIT. It's so if you have a fixed number of threads, say 2, then it's a POSIT of witness. So this one layer or maximum size of the article is 2. Now there is an interesting result which came in Fox 2015, where the result said that if you have any first order sentence that you want to check of POSIT bounded width. In general, of course, first order model checking is of the order n to the length of the sentence, O of the length of the sentence. The vocabulary here is less than, and then I suppose the events, the POSIT relation, POSIT less than, and I suppose it's also labeled POSIT. Is it labeled POSIT? It's also labeled with a finite with fixedly many labels. Yeah, okay. I see. It's okay. So if it was explicitly defined, we'll see what can. But the result says that if you have any first order condition that you would like to check of POSIT upon width, then you can do that in time some function of the length of the sentence times n squared. N squared is the length of the execution, or the number of elements in the POSIT. It's very large, right? Yeah, that is a, and the width is bounded by say some number k.
Or
no matter what,
screen only,
and no matter what sentence you take, the time that it takes to check that sentence off this POSIT is of the form some function of the width, comma the size of the sentence multiplied by n squared, where n is the length of this is the number of elements of the POSIT. It's a generalized question to dense setting. Yeah, this was in Fox. Yeah, but so I was wondering if this way, for any first order sentence, all first order sentences. No, this is deterministic. This one is probabilistic. Is there any time for this particular problem? So maybe this is something that, but of course that condition of implicitly generated things to make sense. Okay, so we'll go on to the next talk. Our next speaker is Sanjana, and she will be speaking to us about Wiki, an optimal stateless model checking based on view equivalence.
Okay, thanks. Okay, right. So I am Sanjana, that's already been spoken of. And this is a stateless model checking technique, and we claim that it's optimal, and we designed it on this notion called view equivalence that I'll be discussing today. So let's start by looking at a concurrent program on shared memory objects X and Y. Here R is a read and W is a write, and these are events from 2 threads. So I am interested in asking if this program satisfies some property. So just to make a clarification, we are not looking at a program execution and asking if this is a property satisfied in execution. We are asking if it's satisfied in every execution. And so one way to do that is to look at all possible interleavings of this program, which are essentially executions of the program. And then if this property is satisfied in each of the interleaving orders, then we can say that the property is satisfied. The problem here is that the number of interleavings may be exponential in the number of program events in the threads. And this is what we popularly call a combinatorial explosion in the program interleavings, which also leads to a state space explosion. So stateless model checkers counter this combinatorial explosion by partitioning the program executions into what are called equivalence classes, such that the executions that fall in the same partition behave similarly to the property. The benefit of this is that now a stateless model checker can examine any one representative execution from each class and still reason soundly about the satisfiability of the property. The problem now remains is how do we define such an equivalence relation that does this partitioning? So there have been various attempts in the past. Classically, this equivalence was defined based on the order of occurrence of racing event pairs, where a racing pair is two shared memory accesses where at least one is a write. So in this program, every pair is a racing pair. And so any different order of execution on these events would land in a different equivalence class. So we have 3 of those equivalence classes shown on the right. A more popular equivalence relation is what is called the reads from equivalence, which defines two program executions as equivalent if each read reads from the same write event. And so if we consider the initialization also as an event, then in these two executions, the read sees, it takes the value from the same write, and hence it can be clubbed in the same equivalence class. So now the stateless model checker has a little less work to do. It can just look at one of these two. Recently, there was this work which bases itself on a reads value from equivalence, which considers values. So there might be reads that read from different writes, but as long as they read the same value, and there's also some causal ordering on reads, which I'll not get into, then we can equate those executions and then just look at any one of them. So this is, in summary, we have finer notions of equivalence to coarser notions of equivalence, and in the process, we are going from defining a higher number of equivalence classes to a lower number. So in this work, we propose a novel notion of equivalence called view equivalence, and we claim that it is at least as coarse as any existing equivalence relation, which implies that for any given input program, it induces the lowest number of equivalence classes, and this positively impacts the stateless model checking effort. The definition of view equivalence is straightforward. It equates two executions that have the same set of read events, and each read events read the same value. No ordering on any kind of events to define it. Now, stateless model checkers, when they see an execution, they recognize the equivalence class of the execution through some orderings or relations on the events. So, for example, under the reads from equivalence relation, there is a reads from ordering between writes and reads, and the classical notion has way more ordering, and the reads value from has a little less ordering. So to understand this causal ordering, let's see this example. In this example, there is this read of X that can take the value 1 from 2 writes. If it takes the value from this write, then there is a causal order between the reads, which is not there if the value 1 is taken from this write. So now, since this causal order is a part of the definition of reads value from, it splits these two executions into different equivalence classes. View equivalence by definition does not consider the causal ordering and clubs them in the same equivalence class. So again, the equivalence, finer equivalence relations maintain a higher ordering, and the coarser maintain a lower ordering is what we have generally seen. To get a perspective, under the classical equivalence relation, this program has 27 distinct equivalence classes because there are various kinds of ordering that are maintained. So any modification to any ordering puts the executions in separate classes. Under the reads value from and reads from, it's the same for this example, it is 6 classes. The equivalence classes are essentially just partitions of executions. So with respect to a property. So no, not necessarily. The property, okay, let me come to a slide where I can, I think, answer you better on this. So, right. So under view equivalence class, as we were discussing, there are exactly 4 equivalence classes where the 2 reads see the combination of the 2 values, 0 and 1. So to better understand this difference, what we did is we put loops over the events of each thread. And we see that when we loop 10 times, stateless model checker under reads value from executes 3.7 million sequences, whereas under view equivalence, we see only 40, and that also we can see a positive difference in the time of analysis. So the question is, which of these equivalences is applicable where, which is akin to what you were asking. So if we are looking at properties that can be presented as assert conditions in the program, then that is something that view equivalence is equally applicable to all the previous kind of equivalence relations. However, if we are interested in properties such as race detection, then for that we need to go all the way back to the classical notion of equivalence. All the coarser ones, including reads from and reads value from, cannot do that. So this is the kind of property that we are interested in. We are looking at properties that are presented in the program as assert conditions. Sorry, I'm consistency of. So as far as the equivalence is concerned, it is defined on the executions and any execution. So when we come to the consistency, it is something that is tied to the stateless model checker. So if this equivalence relation in itself is the memory model oblivious. It's the stateless model checker that you would define. So I would come to my stateless model checker and maybe discuss it then. All right. Classical equivalence would be all Mazurkiewicz traces. Yes. So where Mazurkiewicz is defined on some dependence relation, and typically in practice that dependence, so Mazurkiewicz doesn't define the dependence, leaves it as a dependence relation. So in practice, it is mostly defined on racing event pairs, and that is why I just said racing event pairs in my presentation.
Dependence is not just
No, independence would be, so we are talking about equivalence of executions, not of events in thread. So now we have made them linear. And now after the linearization, if all the racing event pairs are occurring in the same order, then we equate them. So that is now a stateless model checker aspect. As far as the equivalence relation is concerned, it doesn't concern with what kind of events there are, because most of these are defined on either the reads or the values that are read or the order of racing events. So these definitions don't include synchronization events as a part of the definition.
Model is going to define the sets that goes into each class. So these sets will keep changing.
Right.
The moment you change memory.
Agreed. So what I meant is that the definition of the equivalence relation itself is not, so the sets that would be formed would be, so it's the set of executions that is going to vary under different memory models. That's the entire set. But how I partition them, which definition I take, the definition will not change for sequential consistency or for TSO or any other. So like intuitively, if we consider the various program outputs or outcomes of assert statements or SSFI nodes, they are all dependent on the read of some shared memory access. And so if we consider all possible values for these reads, then we are essentially considering, we'll not miss any program outcome or any outcome of the assert statement or any program branch. And that is why it is still sound to just consider values and nothing else on top of it. So there's obviously a flip side to the story. And the flip side is that in not considering the additional ordering, we increase the non-triviality of a stateless model checker that is based on a coarser notion of equivalence. And to understand that, the first thing is that stateless model checkers are not aware of the equivalence classes a priori. There is no oracle that gives it to them. So they need to discover it on the fly during execution. And discovering equivalence classes is as hard as doing stateless model checking itself. So what stateless model checkers typically do is that they explore an execution, they study the occurrence of events in that execution, and then try to manipulate the order of occurrence such that in the next, after the manipulation, the next execution has a different ordering and falls in a different equivalence class. And they keep repeating this process till there is a there is some execution, some representative execution explored for each equivalence class. So now let's take this example. In this example, this write writes the same value as the initial value. Now under the reads from equivalence, a stateless model checker would see that there is a reads from occurring right here, and then would try to change this read from, and that will ensure the execution of a different equivalence class. Something like this. So by manipulating their order, the reads from has changed to a read from initial, something like that. However, under a coarser notion like view equivalence, there is no distinction between the initial and this write. So this is fine as long as the stateless model checker is smart enough to recognize that there may also be outcomes of this nature which are not possible with this RF. So a stateless model checker needs to be designed to be able to recognize this and to be able to make the manipulation and come up with an execution, something like this, so that outcomes of this nature are not missed. So essentially what we are increasing is the complexity or the non-triviality of stateless model checkers. So on this end, with the finer notions, there is more information for constructing coherent ordering for subsequent executions. But on this end, we have lesser information, and this needs to be done operationally. However, if a stateless model checker can manage the same, then we see savings in the time of analysis and we see better scalability. So we propose a stateless model checker. We call it Wiki. And it is for a single input and deterministic terminating programs. We claim soundness, completeness, and also optimality, in that it only looks at exactly one program execution per equivalence class. I'll not go into the details of the stateless model checker, but this has been implemented over NIDHUG framework from Uppsala University, and we tested it over 16,000 plus tests. We found this, we compared it against various existing stateless model checkers on various finer notions of equivalence. And we found a set of benchmarks where increasing the problem size in number of loops or the number of threads does not increase the equivalence classes under view equivalence, and we see huge savings. We also saw benefit with benchmarks which have many writes but few values. We saw huge savings over there. And also benchmarks that have quite a few writes but few reads. And if there are no causal dependencies, then we also see RFSC, which is on reads from and reads value from, also perform better, but we saw view equivalence outperforming them. We saw that that Wiki also performs quite well on mutual exclusion benchmarks. On the other hand, we found these benchmarks where the number of equivalence classes remains the same under various definitions of equivalence. And there we saw the opposite result. We saw this stateless model checker based on the classical notion perform much better than all the coarser ones. And this is where that non-triviality is seen in practice, because analyzing one execution for coarser notions takes more time, and the savings are because they are looking at lesser number of executions. So for future work, we are currently working towards developing, extending this for weaker memory models. We could possibly coarsen, but we are not looking at that. We are interested in looking at its applicability to transactions and also support richer constructs. Scalability is a challenge for stateless model checker, and it still remains beyond view equivalence. So there are these smaller benchmark slices of bugs in FreeBSD, NetBSD that all techniques can manage. But there are also benchmarks like SafeStack, which none of these techniques can still scale to. So thank you for listening. I'm open to questions.
I think we may have time for just one question. Yes.
Why are we doing optimal?
Why do you call it optimal?
Why do we call it optimal?
Yeah.
Traditional reasons.
Okay.
Because there are
no,
stateless
like,
model check. Sorry?
There is no theorem saying that this is somehow maximum.
No, we do have a theorem. We do state optimal, but the way that we state optimality is that we execute exactly one execution per equivalence class. And this definition of optimality is been going on in stateless model checkers. This definition does not come from us.
So in this respect, the other equivalence definitions are not optimal, or are they also?
The
optimal?
definitions themselves are not optimal, but the stateless model checker. So the definition would partition executions in. So we have a set of executions. We've created partitions. Now it is mandatory to look at least one from each, but redundancy only adds to overhead, but it's still sound. But that overhead we would want to reduce. So to reduce the overhead, then there is where optimality comes in. Thanks.
Thank you, Sanjana, for the talk and for the questions from the audience. We'll have our next speaker coming in, Aditya Sharma. Okay, our next speaker is Aditya, and Aditya Agrawal. I'm sorry, and he is going to talk to us about UWOMP. I think he would help me with that. It's extending.
Excuse me.
It's implemented version with point-to-point synchronization, reduction, and schedules. So looking forward to hearing from you.
Sorry. Yeah, I think it's. Thanks. Okay, so good afternoon, everyone. My name is Aditya Agrawal, and I am from the PACE Lab Department of CSE IIT Madras. I will be presenting my work on UWMP Pro, extending UWMP++ with point-to-point synchronization, reductions, and schedules. I worked with Professor V. Krishna Nandivada, and this work was published in PAC 2023. So first, let's look at very basically what is OpenMP. Very brief, OpenMP is a very popular parallel programming API that allows you to add parallelism in sequential code. And OpenMP works on something called a team of workers model, a worker or a thread, which call it interchangeably, where a thread is given a set of tasks to execute. And synchronization occurs among the workers and not among different iterations of a parallel for loop. So let's take an example of a parallel for loop, and there are some set of n iterations shared among different workers or threads, and each worker or thread executes a set of iterations. That's why we also call it a OM OpenMP model or a one-to-many OpenMP model. And each iteration we term it as an activity, and synchronization can only occur among the different threads and not workers. There was a prior work done titled Efficiency and Expressiveness UW OpenMP by Allur and Nandivada. The paper was published in Compiler Construction. They coined the term called unique worker model. Now, what is a unique worker model? It's contrary to what in the earlier statement when I said unique worker model would mean that an OpenMP parallel for loop is said to be executing in a unique worker model if each iteration is executed by a unique worker. Okay. So now when we looked at different benchmark programs in different benchmark suites, we found out that there are something called stencil computations where you are not synchronizing every iteration with every other iteration. You will only more naturally specify synchronization among a neighboring iteration. For example, if I am an iteration I, and let's say I want to synchronize with two iterations I-1 and I+1, then that would be a better way to, then that would be another level of synchronization that I can specify compared to me just synchronizing with everyone else who are not part of the synchronization objective. So with this motivation, we designed UWOMP Pro that allows synchronization among different activities. So, correct. So let's say there are 1,000 iterations of a parallel for loop, and in the earlier scenario, when you want to synchronize among the iterations, you would want to synchronize among different threads. So each thread is running, let's say, thread 1 executes 250 iterations, thread 2 executes another 250 iterations. You can synchronize among the different threads or workers, but not among different activities. So when it comes to unique worker model, we try to give an illusion to the programmer that each iteration is now being executed by a unique worker. So let's say, I'll give an example that will explain it better. But again, now synchronizing among all different activities is something that is not required for Stencil computations, as I said. So maybe look at an example, and that would be, so now let's look at why we want to motivate on people using point-to-point synchronization, right? Let's look at this very simple code on the top left. It consists of a parallel for loop. There's a header, the statement S1. Let's say we want to synchronize at line number 4. And there's a statement S2 after that. It turns out in vanilla OpenMP, which is the traditional OpenMP present today, you cannot actually specify any barrier synchronization inside this work sharing construct. So let's say if you still want to do it in OpenMP, the vanilla OpenMP, you would do something like this, which is you have your for loop, you have statement S1, there is a barrier at line number 5 that will allow you to synchronize among these different statements. But can you do this always? Is one of the questions. Turns out you can't, because if there is, let's say, a dependence between statements S1 and S2, then you cannot just break, or you cannot just loop fission, we call this. You cannot just do this do this thing. So with this only, the prior work, the motivation for prior work came in, and now UWOMP++, which is unique worker model of OpenMP++, allowed barrier statements to be inserted inside a parallel for loop. Now, as I said, this is a good improvement from the previous scenario, but still, let's say I want to only synchronize between 2 iterations, I-1 and I+1. Now, how did UWMP Pro kick in? What we now do is we use something called signal and wait functions, where if I am an iteration I will signal my neighboring iterations I-1 and I+1, and I will wait for a signal from the same iteration space that I want to synchronize from. And what is E? Hold on, in the next slide, we will explain what is E. That will be a better example in this scenario. But basically what I want to say here is signal and wait functions. I want to signal some set of iterations, and I want to wait for a signal from the said iterations. Now, right, it's a parallel for loop because the for loop is annotated with a preprocessor directive like #omp for, by which you can convert this loop into a parallel for loop. That's the crux of OpenMP in this example. So, reduction. So, we believe reduction was already present in OpenMP much earlier. Then why are we again talking about reduction in a whole new scenario? Let's look at this with a very small example again. It consists of a for loop with a header. There is a convergence condition while set of differences, sum of differences, d is less than equal to some epsilon. Then I want to compute the new value of b. I want to compute the difference between the b and the older value, which is the value present at a. Then there is a barrier. Now I'm talking about in terms of UWMP++ only now. OpenMP, though you can't do it, but for UWMP++ you can actually. So if you read the comment at line 7 and 8, it explains why you want to put the barrier at line 6. Why you want to put it? Because you want to wait for all activities to compute their respective values of the diff array. And then one of the activities, which is I equal to 1 in this scenario, will do the summation of all the differences in the function at line number 10. And then there's a pointer swapping for the next iteration. And if you look carefully at comment 14 and 15, it says the barrier is added there because activity 1 or iteration 1 is performing the difference. And what will the other threads do? Other iterations do? Other iterations will wait at the barrier at line number 13. So if you read the comment carefully, this is what we wanted to do here, and this is UWMP Pro. So I have grayed out the portions of the code that is common. Now, what we also support here is when we want to synchronize, that is at line 6, when we synchronize, we throw in our value, which is our diff I value. Let's say if I'm iteration I will throw my diff I value to all my iterations. And that forms my synchronization here. And I will wait for a value from all iterations for their value of diff. And then I will do a reduction. That's why it's called wait all reduction. And I will, the D denotes the synchronization variable where I want to put the reduced result, and add denotes the reduction operation I want to perform. Now, there could be some scenarios that you would still want one of the activities to perform some synchronization. In this case, some operation. In this case, activity 1 still performs a pointer swapping, which is line 8 to 10. But if you look at line 11, 12, this is where the conditional or the expression E comes into play here. If I am I equal to 1, which is if I am activity 1, I will signal all the activities. So you can see there's a condition I have attached to the first parameter, signal all activities if I is equal to 1. And in line 12, if I am not I equal to 1, that is the first condition of wait, I will wait for a signal from whom? I will wait for a signal from 1. So in this level of expressivity that you can specify in OpenMP using UWMP Pro is something that we have designed in the entire this research work. So now, 1 means it's always true. So if I want to, let's say I want to synchronize with everyone else, and I don't have any condition if I'm let's say in iteration, I'll just specify 1 as a true value. Always you need to synchronize in that scenario. So we already motivated about point-to-point signal reduction. I will talk about what commands we support in UWMP Pro. I'll talk about how we actually do something called a continuation passing style transformation of a given input code. We designed a novel runtime support to support the synchronization objective, implementation evaluation, and conclusion. So these are the commands that we support in UWMP Pro. First 2 set of commands are signal wait and signal all wait all. The signal wait targets 1 or more activities, while signal all wait all targets all activities. We kind of made this because you do not want to enumerate all activities in a signal call. That would be not a pleasant experience. So that's why we had signal all and wait all, that will just signal all the activities. Similarly, the reduction counterparts are signal send wait read for 1 or more activities, and signal all send wait all read respectively. Now, this transformation of code to a form which we call continuation passing style was also inspired by the previous work, which was UWMP CPS. And the natural reason why we want to do a CPS transformation is we want to support wait and continue. Maybe I'll just go to an example that will explain it better. But in Crux, what we try to do is in UWMP CPS, they were converting the entire program to CPS form. We later realized that we do not have to actually do that overhead, in the sense we only want to convert those functions that are reachable from a parallel for loop. So we try to minimize this overhead, and we call our extension called UWMP CPS Pro. Let's look. So this is a rough block diagram of our translation. We have the UWMP Pro. We put it into something called a simplifier module that abstracts out many of the language features or the high level abstractions. Then we put it in the CPS translator module that outputs a UWMP CPS Pro code. And then the OM OpenMP translator will give you the final OM OpenMP code that you can compile using any of your favorite GCC compiler or any compiler that you have in the market today. So we'll look at a quick small example of how we do this CPS transformation. Consider this small code where we are S1, signal, wait, and S2. What we do typically is we move first. So the flow of the code would be, I would execute S1. Let's say I'm in iteration I. Then I will signal to I minus 1, I plus 1. That is one part. Then once that is done, I will execute the function that executes the next part, which is to wait for the activities mentioned here. And once that is achieved, I will execute fun2, which is executing statement 2. So if you look at it carefully, what we do is at line 5, we call signal CPS, which is a CPS counterpart of the signal function that our translator will do it. And then the first argument is a closure K. Closure just wraps what function has to be called after you have executed that function signal CPS. In this case, it's fun1. And if you go inside fun1, it creates another closure that calls a function fun2 after wait CPS that executes S2. So this way, our continuation allows us to execute the function only when the synchronization has been achieved. So, and then finally, once we have this code, we convert it into OM OpenMP, where we again enumerate the body of the parallel for loop to a function, in this case fun, and the same thing, like in the line number 3 on the top, we wrap that call to the function fun in a closure K, and we put it in the work list. Now, a work list is something very simple, very simple. I'll just explain in 1 minute. So work list, what it does is, think of it like a bucket. There's an iteration I created the closure K, which means I want to start executing the function fun. I will put that closure K inside a bucket. And when I'm trying to execute my function, which is at line number 6, execute the work list, I go to that bucket, see that, oh, there is a K that I have to execute. I'll just take that K and start executing. Now, why do I have an execute work list? It depends on the scheduling policy that you have specified. If you, let's say, OpenMP, as we all know, supports 3 scheduling policies: dynamic, guided, and static. Depending on the scheduling policy you specify, we call the appropriate execute work list function. We have made our own implementations of the same schedulers as well. Now we quickly look at, actually we talked about how we translate the code, but I never talked about how we actually do the signaling part, right? So let's say this is an activity 1. It wants to send a signal to activity 2 and activity 3. In this case, activity 1, what it does is, it sends a signal to, also what we do is typically, let's say if I am activity 1, I want to synchronize with some activity 2, I'll go to that place. There's something called a post box we associate with each activity. It's, let's take an array of n elements. And when I want to signal activity 2, I go inside the post box of activity 2 and I encode the signal, enqueue the signal from activity 1. And what does it happen when the activities are trying to wait? So activity 2 was waiting for a signal from activity 1. It goes into its post box, sees that, oh, there is a signal from activity 1, and synchronization is achieved. Similarly for activity 3. In an unlikely scenario, let's say activity 1 has not yet signaled. Sorry. Yes, it dequeues. So we have a enqueue dequeue logic, which is a queue we use. So it's like when I'm trying to signal, I enqueue. When I try to receive, I dequeue. So yeah, it deletes it actually. Yes. So in an unlikely scenario, when let's say activity 1 does not yet signal activity 2, what happens? So activity 2 comes, sees there's a post box sees its own post box, sees, oh, there's not a signal from activity 1 in this case. So what it does is, activity 2 will just suspend. So what we do is, we again push it back to the work list, and the thread that was executing activity 2 will execute some other activity which is present in the work list. If it is not present, then it will keep on busy waiting on this activity. But what we use something called suspend, which is, we suspend that activity 2, try to execute other activities in the work list, and then come back later on to see if there is a signal from activity 1. So we have the work list. So when we are executing activity 2, we saw that there is no signal. So we again enqueue it back to the work list, and we execute the other work list. So it's a queue again. So the work list is just a queue. So it tries to execute the other closures, and then when it comes to activity 2, it sees that, oh, I have to again come back at this point. We try to save the program point where it has to come back also. So that's how this thing is done. Now, so quickly going through this. So again, as I said, postbox is associated with each activity. Hence, we can say the postbox is an array of n elements, where n denotes the number of activities. Each entry of the postbox is nothing but a hash map of k elements with a load factor of m%. This is just to do rehashing and better collision management systems. So this is a typical example of a postbox. And quickly going over how do we do reduction. We have 2 algorithms designed for reduction. One is the eager reduction, which is, if I am synchronizing with 2 activities, let's say only, and I want to also reduce the values that are sent by those activities. Just a minute. So I want to reduce as well. I will get the message and I will reduce straight away. But in terms of lazy reduction, I want to do something called an all-to-all reduction, let's say, where it performs something called an exchange-based protocol. And this is a simple example of an array of 8 elements. Reduction operation is add, and activity I first exchanges neighbor, then the next neighbor, then the next neighbor, and finally the last iteration. You can see that all the elements of the array are having the reduced value. We'll quickly go over implementation. The translator we wrote in the IIT Madras OpenMP compiler framework, developed in-house, and the runtime support we wrote in the C programming language. These are the benchmarks we use to test our code, and we test our solution across 3 dimensions. This is to evaluate all the all-to-all based kernels, which is kernels having all-to-all synchronization. This is evaluation for all point-to-point based kernels to find whether it really helps us to get better against OpenMP. And this is when we evaluate against the reduction based kernels. And in summary, UWMP Pro supports point-to-point synchronization, reduction operations, and all the scheduling policies of OpenMP. We use the CPS format to efficiently realize this wait and continue operations. And UWMP Pro presents a novel subsystem by which you can realize this objective. And we believe by using UWMP Pro, it adds as a new parallel for people to have improved real expressiveness and performance when you start writing your OpenMP programs. Artifacts are available for you to play at this link, github.com/artifact-pact. And with this, I conclude my talk. Thank you. Please.
On this, yeah, a very quick question because we are.
I'm just curious about how efficient your closure forming at runtime is. I mean, there's this Andrew Appel had this idea of doing configuration passing,
Right.
passing style.
Right. Right. Right.
So I can understand you don't need to make this pack in everything into the
Correct.
configuration.
Right.
Threads that don't matter. So how what's this format of this closure record?
So closure has 4 formats. One is the function that I want to execute. Second is the environment required to execute that function. The third one is the type of closure, whether this is a synchronization operation or not a synchronization operation. And the fourth one is the continuation. It's like a linked list. So we.
Because you seem to be doing that. Are you doing that at the file type or isn't it file type configuration?
No. Right. Correct.
Some of them seem to be created at runtime, which is what I.
Okay. So let's take this example. So previously, what we were doing was we were creating make closure that you can see in the line 4 and 8 in this case are functions that create the closures. We see that overhead, but what we do is we replaced it with a preprocessor macro. So it is just there's a structure. We just populate the fields one by one. I just abstracted out for the slide here. The low level details I have not presented, but at the present, what we use is a macro that will just fill up. Okay, the first field is fun1, second field is the environment, third field is the type, fourth field is the and what type to fill. We have not measured the overhead, but yeah, that's actually a good thing that we can do.
I think this may be a good point to stop. So let us thank the speaker. Nice talk. Always continue the discussion over lunch. So we will break for lunch now. And I think the next talk is at 2. It's an invited talk of FST. So yeah, about enough. Downstairs. Yeah. The invited talk. So what? 10? 105. 105. Yeah. Yeah. So the invited talk will happen at the usual venue, 105. The venue, the usual venue. Downstairs.
Hello, 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 hello. 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 ఎంత లేట్ ఉంది హలో 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 Hello, 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 hello.
Turn it off. Check, check.
This is on, right?
I know. So check, check, check. Like it doesn't work over here also.
Pritam Karat, yes.
All right, we have another exciting session for today. Our first speaker is Pritam Karat. She will talk about resource management specifications. She is right now working at MSR. With that, the floor is yours.
Thank you. Good afternoon, everyone. In this presentation, I'll be talking about a fully automated static resource leak checker that uses resource management specifications. This work was published recently at UPSLA. So the talk basically has two main sections. The first section being an overview of the past work, where I'll be describing what are resource management specifications and how a resource leak checker uses the specifications to detect resource leaks. The second section is the most important section because it covers the current work, which is inference of these specifications, followed by the evaluation and then the conclusions. So a resource leak occurs when a program fails to release a resource after it is no longer required. In languages like Java and C#, resource management is a joint responsibility between the developers and the runtime environment. Managed resources like memory are taken care of by the runtime environment, whereas unmanaged resources like file handles, network sockets need to be explicitly managed by the developers. Resource leaks may lead to resource starvation, performance issues, and in worst case, whole system crash. Resource leaks can be hard to detect because they do not manifest themselves immediately, but rather over time as the program continues to run. Hence, detecting resource leaks is a critical problem. We have developed a resource leak checker as part of the checker framework for Java and for C# code using CodeQL. This past work was published in FSC 2021. Our resource leak checker is both modular and sound and is based on checking resource management specifications. I'll be talking more about this with the help of an example in the next few slides. It is also lightweight because it does not require whole program alias analysis. Just local alias information is sufficient. Specifications are written on classes and method boundaries. They essentially capture the interprocedural data flow. They help RLC to track which objects control a resource and the flow of resources throughout the program. They also help to improve the quality of warnings generated by our resource leak checker. We'll talk more about this with the help of an example. The past work required developers to write these specifications manually. But with this current work of inference of these specifications, our resource leak checker is now fully automated. As part of this work, we also compare the handwritten specifications and the inferred specifications, and we evaluate our resource leak checker with respect to these inferred specifications. So let us start with an example. In this method, getSQL connection, a resource allocation is performed on line 3. And a reference to that resource is returned on line number 5. In method perform action, there's a call to getSQL connection. As a result, connection is now a new reference to the same resource that was allocated on line number 3. And this connection is now passed as an argument to close connection. Inside close connection, there is release of the resource happening on line number 15 through the parameter con. So this particular C# code snippet doesn't have any resource leak. However, if I were to perform a modular resource leak analysis, by modular, we mean that the analysis is performed for one particular method. And if there are no specifications, there's no information about what other methods are doing, then resource leak analysis would report a potential resource leak on line number 3, which is sound, which is that it doesn't miss any resource leaks, but imprecise as in this example. So let's try to add certain specifications. So we add owning specification. I'll talk about what does owning specification mean. So if there are multiple aliases which refer to the same resource, this owning specification denotes which alias is responsible for releasing the resource. So for this example, we have added owning specification on the return type of getSQL connection and to the parameter con of close connection. Let us perform a modular resource leak analysis using these specifications. So in getSQL connection, there's a resource allocation happening on line 3. Resource is being returned on line 5. However, there is an owning specification associated to the return type of this method, which indicates that the obligation of releasing the resource is being transferred from getSQL connection to its callers. Hence, no resource leak is reported within this method. Now in perform action, remember that we are performing modular analysis. So we'll not be looking at the body of getSQL connection, but just the signature of that particular method. And there we notice that there's an owning specification associated to its return type, which means that a resource is being returned. And this line number 9 now acts as a resource allocation point in method perform action. Connection is now. Because this owning on the return type indicates now that the responsibility of releasing the resource is on the caller. So wherever it is being returned. So here, that's the reason why line number 9 is considered a resource allocation, because the resource is returned. Now connection is responsible for releasing the resource. This connection is now passed as an argument to close connection. Again, we do not look at the body of close connection, but simply the owning specification, which is added to the parameter con. And so in this case as well, the obligation of releasing the resource is now transferred from perform action to close connection, and no resource leak is reported within this method. In close connection, the owning specification on the parameter indicates that con indeed holds a resource, and it is being released on line number 15 by calling close method. In this case, the obligation of releasing the resource is being satisfied. And this is how we perform a modular resource leak analysis. Yes? On line 14, it means that con is holding on to a resource and it is the responsibility of that parameter to release the resource. So either it can release the resource itself or it can transfer this ownership to someone else.
It means con is holding a resource.
Yes, and it is the responsibility of con to release the resource as well. I mean, you just call a close basically you call close function on this particular instance, on this particular reference. So you use this reference to release the resource.
I guess my question is similar to what are the principles? Are they processes or are they data objects?
They are references to those resources. So aliases, basically, you could have multiple aliases referring to the same resource, and owning basically tells you like this is the alias and this is the reference that should be used to release the resource.
Do you have to do alias analysis simultaneously?
A local alias analysis. So the analysis is modular. We need local alias information within that particular method, not the whole program alias analysis.
What about these type states? It's like a type state.
Yes.
These type state techniques don't.
So these are not completely, I mean, these are, we call them as pluggable types basically. They're merely basically, they tell the resource leak checker some information about how the resources are being transferred along the program.
So maybe you can answer this later, but is there some ownership type similar to Rust that these?
Yeah, so in Rust, the ownership kind of.
Go ahead and then at the end.
No, maybe I'll right now answer it, because in Rust, the ownership is kind of imposed. Here, it's just a mere suggestion to the resource leak checker that this resource release should happen because with respect to this reference. Checker framework, yes.
So add non-null annotation is very similar to your add.
Yes, so as I mentioned that this is part of the past work, it's based on the past work on the checker framework, and we have a similar one built using CodeQL for C# code as well. So recall that we also talked about improving the quality of the resource leak warning that was generated by the resource leak checker. So for that, let's assume that there is no call to close connection on line number 11. In this case, this modified code snippet indeed has a resource leak. The resource leak checker will report a resource leak on line number 9 instead of line number 3 where the actual resource allocation happened. This is because of this owning specification over here, which says that the resource release of the resource needs to be performed on the callers of the GetSQL connection. And hence, this is the location where the resource leak is reported. And this is also the location where the developer needs to fix this resource leak. And so the quality of the warning basically is associated to the location at which this particular warning is reported by the checker. RLC also uses this following resource management specifications. We'll take a look at this in the inference section. For more details, please refer to the paper. So as I mentioned earlier, that earlier resource leak checker expected developers to write these specifications, which is a huge hurdle for legacy code. And manually incorporating the specifications is a very time-consuming process. It took us several weeks to annotate a moderately sized program. We do not expect developers to do the same. And this motivated the need for inference of specifications. So these specifications must capture multiple interrelated properties like ownership of the resources, aliasing relationships, and our algorithm employs an optimistic approach such that the specifications that are inferred closely align with the developer's intent. We'll take a look at an example in order to understand this optimistic approach. Our algorithm is a set of inference rules very similar to the data log rules. The inferred specifications, the specifications are inferred by applying these rules to reach a fixed point. The inference rules are generic such that we implemented them in checker framework for Java and also for C# code using CodeQL. So let us take an example where you have a cleanup method which takes one parameter socket. Now this cleanup method does not necessarily close socket because on line number 3 there could be a potential exception, socket exception. As a result, in case of an exception, line number 4 will not execute and there might not be a release of resource. Now in the standard approach, if it reflects only the code's behavior, then no specification will be added to this cleanup method, which may result into many false positive alarms within the callers of cleanup. our optimistic approach tries to mirror the developer's intent. As you can see, the developer actually intended to release the resource within the cleanup method. However, it failed to handle the exceptional case. In this, so our algorithm basically infers owning specification on the parameter socket, and our resource leak checker issues a warning within the cleanup method, which is the location where the bug needs to be fixed by the developer. So let us take a look at the inference rule that is used.
Adding those annotations, you don't expect them to be added.
Sorry?
Those annotations are added by your tool. I thought programmer adds those annotations.
So the earlier work required the developers to write it, but with the inference, we are inferring these specifications, and the resource leak checker can use those inferred specifications.
By specifications, you mean those annotations?
Yes, those annotations. Yes, the attributes basically for the C# code. So you can add them to the code. What we did for CodeQL is basically we added those information in the CodeQL query itself so that we don't change the code and rebuild the code again and again. So let us take a look at the inference rule. So this rule infers owning specification on parameter P of method M, provided that these three conditions are being satisfied. So the first condition checks whether the type of parameter of method M is a resource type or not. So in this case, the type of parameter socket is this socket. And for C#, any type that implements iDisposable interface is considered to be a resource type, because if a type implements iDisposable, it has to define a dispose method, which is generally used for disposing the unmanaged resources. And the second condition, so socket basically implements iDisposable, hence it's a resource type. This rule also expects a must call specification, which takes one argument on this type socket. So we model this specification. So this is the specification that we add for this particular library type. What does the specification indicate? That every instance of socket must call close in order to release the resource. So this close actually closes the socket and internally calls dispose to release the resource. So every instance of socket must call close. This specification needs to be added to the type, which we have added. And the last condition is that there should be an invocation along, at least along some path. May not be all paths. That's the optimistic approach that we take. And if there is, so on line number 4, we can see that there is a call to close method, which was added as an argument to the must call specification that we had within cleanup method. And hence, since all the three conditions are satisfied, we infer this owning specification for this parameter socket of cleanup method. S is the statement. S is the statement in which this particular method is invoked using P as the receiver object within method M. So M is cleanup, MPD is the close method, and M is cleanup, and P is the socket. Optimistic is because we consider it should exist. We do not consider all paths like we do for resource leaks. Then there'll be a warning related to that as well. So if there are two instances of a class which contains this cleanup method and one instance calls cleanup, then there'll be no resource leak in that case, but there'll be a resource leak for the other instance.
If there are more people cleaning up than their resources, why is there resource leak?
So because those are two different instances, so two different instances will have two resources. Let us take a look at another example where we'll talk about other specifications.
This requires the pointer analysis.
Yeah, alias information, again, local alias information. Maybe this example would answer that question. Let's get into this example. So this example has socket wrapper, which has a field socket. It has a constructor which takes one parameter S, which is used to initialize the field, and a dispose method which releases the resource. There's class demo which instantiates socket and socket wrapper. Now in this case, this class socket wrapper, basically you pass this socket as an argument to this, and there's an aliasing happening over here. So you need to remember this aliasing relationship. I'll talk about this, how we do that using specifications. So these are the specifications. We'll take a look at them one by one. So let's first take a look at the call specification. So dispose method is responsible for releasing the resource by calling close method on the field socket. And since when we perform modular analysis, we do not look at the method body. We indicate this by using the call specification, which takes two arguments. The first argument being the reference, which should be used for releasing the resource. And the second is the close method, which is used for actually releasing the resource. So in this case, socket is the reference, hence the first argument, and close is the second argument. Now, as we can see that the field socket is being used for releasing the resource, it is actually the owner of the resource. And hence we add an owning specification on this field. Recall that we had used owning specification on the return type and the parameter. Now we are also using it on the field. This must call specification we had seen earlier takes one argument. It indicates that every instance of this class socket wrapper must call dispose in order to release the resource that it may contain. The resource alias specification is added to the parameter type and to the return type of this constructor socket wrapper. It basically captures the aliasing relationship between the parameter and the return type. So if you take a look at the caller on line number 17 for this constructor, SW and SOC are basically multiple references referring to the same resource. And you can use any one of these references to release the resource. In this case, we've used the instance of socket wrapper sw.dispose at line number 19. So these are like kind of aliasing information. We capture this by using resource alias specification. Yeah. So it depends whether the destructor. So if the developer writes, a destructor, defines a destructor, then it should call dispose within the destructor. Yeah, I mean, it depends how the code is written. So we infer specifications based on the code that's provided to us. Yeah. All right, so maybe I'll just take this particular example for inferencing of the rules. So in this case, dispose method uses this field socket. So we need to first check whether this field is disposable or not. For that, we first check whether the type of the field is a resource type or not. We have checked that socket is indeed a resource type, and that it should have a must call specification associated with that type. So socket is disposable. In order to infer this call specification on method dispose, it first checks whether that field is disposable or not. We have checked that it's true. And the second condition is it checks whether there's an invocation of this close method on the field socket in statement S. And as we can see, it's done on line number 11. So second condition is also satisfied. And after the release of the resource, there's no reassignment to the field. That means there's no new resource being allocated. If this condition is also satisfied, then we infer call specification on method dispose. So this is one of the many rules, inference rules that we have. I'll skip these because of the time constraint. Yes. When we do it at the interprocedural level, it is must alias. Yes. So these are some of the inference rules. Please refer to the paper for more details. Let's get to the evaluation section. So we compared the handwritten specifications with inferred specifications, and our algorithm achieved an 82% recovery rate for open source C# projects and 74% for open source Java projects. It was able to infer all 100% of the specifications for proprietary C# microservices. And our hypothesis is that these proprietary code was written under standard coding practices. So with our previous work, we had added these specifications manually. So those specifications we used for comparison. Recovering, we compared how many of these handwritten specifications were also inferred by our algorithm. Yes, we did infer some more, and I'll talk about this by what do we mean by we inferred some more. Then we ran our resource leak checker without any specifications and with inferred specification. And you can see for some of these benchmarks, basically the inference discovers there are more warnings generated by the resource leak checker with respect to the inferred specifications. And this is because inference discovers new obligations that resource leak checker does not check in the absence of specifications. Let's look at the previous example. If we do not add owning specification on the return type of get SQL connection, then this call, all the calls to get SQL connection would be overlooked. And these are the new obligations that were seen only because of the specifications. The true positive rate using inferred specifications is very close to the rate that was achieved using handwritten specifications, which is 28% for C# and 19% for Java. The number, so let's say the total number of 100 warnings were reported by resource leak checker, 28% of them were true positives. Very few warnings were generated because of the incorrect inferred specifications, indicating that the specifications are generally in line with the developer's intent. There were 25% in C# and 27% of warnings in Java, which were generated because of missing specifications. Common causes are non-resource types and mutable fields in Java. Because of the time constraint, I'll talk about the first cause. The false positives would be a minus of this. So this plus this plus this, 100 minus this plus this plus this. So it's like around 7, yeah. Yes. Yes. So in this case, this class fake resource type implements iDisposable. So this is considered as a resource type. However, you can see that in this particular example, no resource is being allocated in the constructor or even in any other method. So the dispose method literally doesn't do anything. As a result, the call to the dispose method remains optional. So a lot of warnings may be generated basically with the absence of this dispose method. However, this is not a resource leak. And we handle this situation by adding something called as must call empty specification. So recall that must call is basically takes one argument which tells which method needs to be called on every instant. In this say, there's no need of any method to be called to release the resource because there's no resource. So this basically tells the resource leak checker that it does not track the instances of this class. And we currently don't infer the specification because it's very difficult to verify it. So this with the manual specifications, with the manual specifications, since it was very effort intensive, we added specifications only to the library types. But with the current work, we were able to add the specifications for custom types as well, thereby improving the quality of the warnings. Yeah, please try out the checker framework for Java and the C# for the C# code, the code kill query. That's the two links. Thank you.
So we do have time for 1 or 2 questions.
So there is some really old work on ownership types and all that. Like, so how does this like differ?
So this is actually based on the old work of checker framework that was published in 2021. And
some 20-year-old work on ownership types also. Yeah. So is that, do you know how it relates to that? Like this Renard, Boyapati, Renard. Yeah.
So I haven't gone through that work, right?
Okay, that's kind of the canonical work on it. Huh? That was ownership types.
The thing is, Rust basically imposes that ownership. Here we are simply indicating that the resource leak checker should assume that this particular reference is the owner of the resource and should be used to release the resource.
So in Java, there is a try with resources, which comes with an auto-closable interface. So in case of a class like connection, which implements the auto-closable interface, along with try with resources, what happens if you annotate it with ownership? Does that take precedence or will this take precedence? Because essentially they try to do the same thing.
So see, with the try with this thing, what is expected is that before that particular reference goes out of scope, there will be a close or a dispose being called. So there's something similar called as using statement in C#. So even if you add owning specification to that particular thing, it indicates that there will be a disposal happening, maybe because of the try with resources or because you're explicitly calling close. It doesn't matter whether you add it to the try with resources or you explicitly call a dispose method or a close method on it.
Oh,
right? Otherwise, yeah.
So when you're adding, for example, a must call dispose. So the reason that you choose to dispose at one,
yeah, it needs to be called recur. So dispose basically should be responsible for all the fields. So let's say your class has multiple fields, then dispose should basically should dispose the resources related to all the fields. Only then I'll add the must call specification. So must call specification contains an argument which releases all the resources in that class. So it may be possible that you have multiple fields and hence multiple resources being stored in those fields. So we'll consider the argument being that method which disposes all the resources, not just one resource.
I mean, this is of course in the C# framework and so on, but is there some connection with old ideas coming from process calculus with name passing, like the pi calculus, where you worry about things like linearity or affineness or relevance and so on? Have you looked at those typing disciplines which come with it?
No, not yet. But yeah,
I mean, those are basically were inspired by linear logic that led to that
Yes.
old ownership types.
Yeah, so that's like we are thinking on in terms of that, yes, but not right now. Yeah.
Let's thank the speaker. Okay, so why don't we take this offline?
Yeah.
Let's thank the speaker again.
Thank you.
Okay. So if Zoom is an issue, maybe for this particular talk, Zoom and then directly.